Let's continue our exploration of derivatives with the chain rule. Before we do that though, let's look at finding a derivative and kind of warm it up. So I really recommend you pause this video, work through this derivative, unpause it to watch me work through it afterwards to make sure that you understand this process. And then we'll bring in the new process of the chain rule. So there's two different ways that I can find the derivative of this. I can either use the product rule, or I can go through and expand this out first, and then I can go through and use the just basic derivative. So let's go through and use the product rule just because we just learned that, and I think it's gonna, more practice we get, the better. So, all right, so the derivative, so if I was using the product rule, I'm gonna write this kind of expanded out. This is x squared plus 2x minus 4 times x squared plus 2x minus 4. Okay, so finding the derivative of the function y with respect to x, so that's going to give us the first function times the derivative of the second plus the second function times the derivative of the first. All right, that's going to end up giving us, so we're going to have that x squared plus 2x minus 4 times, so the derivative of this piece is going to be, so the derivative of x squared is 2x, the derivative of 2x is just 2, and then the derivative of minus 4 is 0. So we'll have the same thing over here, x squared plus 2x minus 4 times 2x plus 2. All right, so now we've got to go through, multiply this all out, so this is going to give us 2x cubed plus 2x squared plus 4x squared plus 4x minus 8x minus 8 plus, and then we'll have the same thing. So 2x cubed plus 2x squared plus 4x squared plus 4x minus 8x minus 8. When I simplify all of this together, we've got, so 2x cubed plus 2x cubed gives us 4x cubed. I've got 2x squared plus 4x squared is 6x squared, 8x squared, 12x squared. So I've got plus 12x squared. And then I've got 4x minus 8x is negative 4x, plus 4x is 0, minus 8x is minus 8x. And then I've got minus 8, which is minus 16. So that wasn't awful. We were able to do it, but there are just a lot of steps in here and a lot of multiplying and simplifying terms where there's a lot of ways that we can make some mistakes. So today what we're going to learn is we're going to learn what is called the chain rule that's going to make these types of functions a lot simpler for us to find the derivatives of. So what if we needed to find the derivative of this function? I'm sorry, but I am not going to expand out that to the 50th power. Okay, we were able to do it to the second power. It wasn't that bad. Doing it to the third power would get a little bit worse, but I am not doing that to the 50th power. So there's one last differentiation rule that we need to learn, and it's really, really important. How can we find the derivative of a composition of two functions? So first, let's make sure that we're comfortable with what a composition is and how to decompose it to establish the inside of a function from the outside of the function. For example, here we can see that if we were talking about inside and outside, we can see that the inside of this function would be this piece. And we're going to always call the inside piece u. And then the outside of the function is going to be something, so like an x. In this case, we're going to call it u since I've let this equal u. So our outside function is going to be u to the 50th power. Because that's essentially what y is. If I'm letting u equal this, I can replace that with a u and rewrite that as u to the 50th. Now, notice u to the 50th, I can differentiate that. That's just using the power rule. So that's what's going to help us when we've got this using the chain rule here, so that we can get it where we can take that inside function out and get that outside into one that we can actually differentiate, and then we'll apply that chain rule. Now, before we do that, again, I just really want to make sure that we have a good solid remember or recall of composition of functions. This is something we learned back in college algebra. So for each composition, decompose it into the inside function and call it u, and then write the outside function as y in terms of u. So if I was looking at this first one, I would say, okay, our inside function is going to be this, so we're going to let u equal that. And then our outside function, now that I've let this part equal u, would be u cubed. Over here, inside function would be 3x. Outside function is the sine of u. So I'm going to ask you right now to pause the video, and I want you to go through and do the inside and outside here, and then when you're done, unpause it so you can make sure you check your answers with watching me go through it. All right, so hopefully you found here, this would be that inside function. So u equals e to the x plus 3x minus 1. And that outside function is the secant of that whole thing, which I've just called u. All right, looking at this next one, our inside function is going to be that. And then our outside function is going to be the square root of that, which again I've just called u. Looking at this next one, our inside function is 7x squared plus 4, so I'm going to let u equal that, and then I can replace that in our formula, so it becomes y equals e to the u. And then in this last one, I'm going to let u equal this piece, and y is going to equal 1 over that, so 1 over u. All right, I think we're at a point where we can actually bring this chain rule in. So given y equals f of g of x, so we have a composition of functions, if we let u equal that inside function, so we're letting u equal that, and then we're letting y equal the function at that inside function, so f of u, not fu, f of u. If both functions are differentiable then, so we can write this using Leibniz notation, so we'd get the derivative of y with respect to x. So right now, if we just were trying to find this derivative, it's a derivative we couldn't find, so something, or it would be really take a long time to find. So like the x squared plus 2x minus 4 all to the 50th power. So if we can split that into two functions that I can differentiate, an inside and an outside, then watch this. So if I take the derivative of the outside with respect to the inside times the derivative of the inside with respect to x. So the reason we can say that those are equal is those would cancel and we'd be left with dy over dx. Okay? So these are equal statements. So as long as we can find an inside function that we can differentiate and then an outside function that we can differentiate, then we're going to be able to use this chain rule. Now, another way to look at the chain rule is as follows, and this is the prime way that to talk about it. This is the Leibniz notation way, and this second one alternatively is the prime way. So basically what we're doing is you go through and you are evaluating the derivative of the outside function. So that outside function with respect to the inside function. Okay, so again, this outside function with respect to the inside function. Then you find the derivative of the inside function. So what we're going to be doing for a little while is I'm going to stick with doing Leibniz notation just so that you guys can kind of see this process, and then we'll switch over to doing it the prime way once you see where everything is coming from. All right, so let's go through and practice using the chain rule now that we know the formula. So find each derivative from slide 4. So on slide 4 for this first problem, we let u equal x to the 5th plus x squared, which meant that du dx was 5x to the fourth plus 2x. And then we let y equal the outside function, which is u cubed. And so dy du equals 3u squared. So when I find this, we learned from the last slide, dy dx equals dy du times du dx. So substituting in those values, dy du is 3u squared. Du dx is 5x to the fourth plus 2x. So now when I substitute in what u is, x to the fifth plus x squared, I get 3 times the quantity x to the fifth plus x squared all squared times 5x to the fourth plus 2x. In the second problem, we let our u equal 3x, so that meant that du dx was 3. And then we let our y equal the sine of u, so dy du equaled the cosine of u. So now when I set this up, I'm going to have dy dx equals, so dy du, which is the cosine of u, times du dx, which is 3. I'm going to write that 3 first, and then I'm going to substitute in what u is in for u, so I get 3 times the cosine of the quantity 3x. And in this last problem, I let u equal e to the x plus 3x minus 1. So du dx equals e to the x plus 3. And then our outside function y was the secant of u, which meant that dy du was secant of u, tangent of u. All right, so when I set these up, dy dx equals dy du, so the secant of u times the tangent of u, times du dx, e to the x plus 3. So now I'll substitute in e to the x plus 3 everywhere I see a u. So this becomes the secant of the quantity e to the x plus 3 times the tangent of the quantity e to the, I'm putting in the derivative. So the secant of u, which was this crazy quantity, so the secant of e to the x plus 3x minus 1 times the tangent of u, so e to the x plus 3x minus 1, all times the derivative of u with respect to x, which is e to the x plus 3. More like second nature. So find each derivative from slide 4. Okay, let's continue going. So here I said that u was 16x squared minus 1, so that's our inside function. Our outside function is the square root of that, so the square root of u. All right, so this derivative of u with respect to x is going to be 32x. And here the derivative of y with respect to x is 1/2 u to the negative 1/2. Okay. So if I were to write this out again, dy dx equals the derivative of the outside with respect to the inside times the derivative of the inside. Okay, so I found dy dx was this, so dy du, u to the negative 1/2 times the derivative of u with respect to x, which was 32x. So that's going to give me 1/2, substitute what u is in for here, 16x squared minus 1 times 32x. And this should be to the negative 1/2 power. All right, next one. So here u equals 7x squared plus 4. Outside function in respect to u is e to the u. Both of these are things that I can actually differentiate. So the derivative of u with respect to x is 14x. The derivative of y with respect to u is e to the u. Okay, so again, dy over dx equals, I'll do this in color coding so you can see it even more. So the derivative of y with respect to u times the derivative of u with respect to x. So now I'll just substitute those in. So I get e to the u times 14x. So that gives me e to the 7x squared plus 4 times 14x. Okay, last one over here. So u equals x cubed plus x. Y equals 1 over u. The derivative of u with respect to x equals 3x squared plus 1. The derivative of y with respect to u equals, so this is the same thing as u to the negative 1. So if I use the power rule there, it's going to be negative u to the negative 2 power. So we can write that as negative 1 over u squared. Okay, so then again, using that chain rule formula, so the derivative of the entire function with respect to x is du dx times the derivative of y with respect to u. Actually, those should have been flipped so that we stay consistent. It doesn't matter, you'll still get the same answer because multiplication is commutative, but just to stick with consistency. All right, so this gives us dy du was negative 1 over u squared, and then I had du dx was 3x squared plus 1. So now we'll put in what u is, so that's x cubed plus x squared times 3x squared plus 1. You can leave it like that, or we can just multiply this as a fraction, and we get negative 3x squared minus 1 all over x cubed plus x quantity squared.